Welcome to a story about the shape of computation. Not just how fast can we solve a problem, but something deeper. How much structure does a computation need just to exist? You can think about computation as speed, wiring, flow, or architecture, but all of these pictures are secretly about shape, how much structure you need just to make the computation exist. In algebraic complexity, there's a question that haunts researchers: VP versus VNP. Think of it like P versus NP, but for polynomials. On the left, VP, like a well-organized factory. Efficient, tractable. On the right, VNP, like a chaotic warehouse. Polynomials that seem to require exponentially many pieces. Watch how organized structure differs from chaos. On the left, the determinant. Neat rows and columns like soldiers in formation. On the right, the permanent. Same formula, but wild and untamed. Here's our key insight. We encode polynomials as quantum states. Why? Because quantum states have entanglement, like invisible threads connecting distant parts. Entanglement measures exactly how much plumbing our computation needs. The slogan to remember: complexity of a polynomial equals entanglement structure of its quantum state. More threads means more complex. Here's the journey we'll take today. Think of it as building a diagnostic toolkit for polynomials. Act 1. How to draw a computation. ABPs and MPS, the blueprints our polynomials live in. Let's meet our first character, the Algebraic Branching Program, or ABP. Think of it as a highway system with toll booths for routing algebra. On the far left, a source, where your journey starts. On the far right, a sink, your destination. In between, layers of checkpoints like a series of toll plazas. Watch as we add highway lanes. Each layer has a certain width, the number of parallel lanes at that checkpoint. More lanes means more traffic can flow simultaneously. To compute a polynomial, pick any path from source to sink. That's one possible route. Each edge carries a linear form, like a toll you pay. Multiply all the tolls on your path, then sum over all possible routes. Watch this golden packet travel along one specific route. At each edge, it picks up a factor. The product of all factors along this path gives one term of our polynomial. The crucial insight: width equals information bottleneck. Think of rush hour. If you have 3 lanes at the narrowest point, only 3 cars can pass at once, no matter how wide the rest of the highway is. Now let's see the same structure through quantum physicist eyes. The ABP becomes a matrix product state, or MPS. Same math, different costume, like seeing a circuit as a pipe system. An MPS is a chain of tensors, like machines on an assembly line. Each machine has an input port at the bottom. That's your variable x_y. Between machines, conveyor belts called bonds carry intermediate results. Watch the information flow through the channels. The belt thickness is the bond dimension d. A thicker belt can carry more information, more quantum channels. Here's the key question. If we cut the conveyor belt at any point, how entangled are the two halves of the factory? How many quantum threads are severed? The answer never exceeds log of the bond dimension d. If your belt has 8 channels, entanglement across that cut is at most log 8 equals 3 bits. The belt thickness caps how correlated the two halves can be. The magical bridge: ABP width equals MPS bond dimension. Highway lanes equal conveyor belt thickness. Same bottleneck, different metaphor. Act 2. How to weigh a computation. Entropy and capacity, finding the traffic jams in information flow. So far, we've learned that width in an ABP and bond dimension in an MPS both limit how entangled the state can be across a cut, like how many lanes on a highway limit rush hour traffic. We keep saying information flow and entanglement. Let's make this precise with entropy, the same concept that measures disorder in physics. Think of entropy like weather forecast certainty. When the forecast says 100% chance of rain, you're certain that's low entropy. When it says 25% rain, 25% snow, 25% sun, 25% hail, you have no idea. That's high entropy, maximum uncertainty. These bars represent probabilities of different outcomes, like rolling a weighted die. The height shows how likely each face is. Here, one outcome dominates. You're almost certain what will happen, like a die loaded to always show 6. This is predictable, low entropy. Now watch this transformation. We redistribute the probability sand from tall piles to equal piles, like unloading the die. Entropy rises as certainty falls. When all bars are equal, every outcome is equally likely. A perfectly fair die. This is maximum chaos, high entropy. You can't predict anything. The von Neumann entropy formula captures this mathematically. Negative sum of p log p, peaked distribution means low value, flat distribution means high value. Entropy measures spread, surprise, uncertainty. Now we arrive at the main character of this story. Entropic capacity, one number that tells you how tight the computation has to squeeze. Think of it as the narrowest point in your entire plumbing system. Imagine rush hour traffic on a highway that narrows from 6 lanes to 2 lanes, or internet data squeezing through a slow router, or water in a pipe that suddenly gets thin. The bottleneck determines everything. Watch this pipe system. Water flows freely through the wide sections. Then it hits the narrow section. No matter how wide the rest of the pipe is, that bottleneck controls maximum flow. Watch what happens as particles approach the narrow section. They pile up, they slow down, some even turn red from congestion. That's what a hard computation looks like. Too much information, not enough bandwidth. Traffic jam. The fundamental theorem, entropic capacity equals log of the minimal bond dimension. Find your narrowest belt, take the log. That's your capacity. E of P equals log of D min. Act 3. How to compare computations. Geometry and tools that prove who's genuinely harder. Width of a layer, thickness of a bond, diameter of a pipe. They're all the same story. How much can squeeze through a bottleneck? Now geometry enters our story. We study orbit closures. Don't worry about the jargon. Think of it as a container or mold. Here's the intuition. Imagine you have a sharp, detailed photograph. You can blur it, shrink it, simplify it, but you can never sharpen a blurry photo. Simplifying operations are one-way streets. Polynomial P defines a container, a mold of possible complexities. If polynomial Q is simpler, it fits inside the mold like a smaller shape. But if Q is too complex, too spiky, it bursts out of the mold, like trying to fit a porcupine into a soccer ball. Q's orbit closure cannot be contained in P's. This gives us our weapon. If the permanent has higher capacity than the determinant, it physically cannot fit inside. Capacity is a volume check. Bigger thing can't fit in smaller container. The key property. Capacity can only decrease as we simplify. You cannot create complexity from nothing. Blurring can't sharpen. Compression can't add detail. Stretching a rubber band can't make it thicker. Here's where the research gets fascinating. We ran experiments on small matrices, n equals 3 through 6. We expected to see differences. We got a surprise. We hit a compression wall. For both determinant and permanent, the entanglement spectra are identical, perfectly flat. At small n, they look exactly the same, like identical twins. Why? The crossover point is around n equals 14. Below that, the naive brute force representation is actually more efficient than the clever algebraic one. The determinant's advantage only appears at scale. It's asymptotic. So how do we tell them apart at small n? The answer, stability. Not what they look like, but how they respond to poking. Imagine two objects, an ice crystal and a water droplet. Both contain H2O, but poke them. The crystal stays rigid, the droplet sloshes. The determinant is frozen, a rigid crystal. Its entropy gauge stays pinned at maximum no matter how you poke it. The permanent melts, a fluid droplet. Its entropy fluctuates wildly under the same pokes. Applying random GLN transformations, like heating or shaking, the determinant barely moves, rock solid. The permanent sloshes around, liquid instability. The determinant is frozen at maximal entanglement due to its symmetries. The permanent melts into low entanglement states under generic operations. This proves they live in different neighborhoods, different orbits. This next section is more technical. If you're comfortable with calculus, here's one last tool. Otherwise, feel free to skip ahead. Shifted partial derivatives, or SPD. Think of it as an X-ray scanner for polynomials. Each derivative is a different angle, a different probe. Each derivative shines a different light on your polynomial, like an airport X-ray showing different cross-sections of your luggage. Watch as each probe creates a unique shadow pattern. On this shelf, each block is one independent shadow pattern. More blocks means higher SPD dimension and a more internally complex polynomial, like luggage with more hidden compartments. The dream chain. Large SPD forces large capacity, which forces large width. Many compartments means big capacity means wide highway. Each step is a proven theorem. The program. Prove the permanent has many compartments. Conclude it needs an exponentially wide highway. VP not equal to VNP. Let's bring it all together with 4 key takeaways, 4 tools in your complexity toolkit. First, the object. Entropic Capacity E measures the minimum information bandwidth across any computational cut. Find the narrowest pipe in your system. Second, the property. Capacity is monotone. Simplifying can't add complexity. You can blur but never sharpen. Third, the connection. Minimal ABP width equals E to the E, 2 to the capacity. Bottleneck size directly determines circuit size. Fourth, the goal. Prove permanent has higher capacity than determinant, or use the stability gap to show they live in different orbits. Either path separates VP from VNP. If you work in complexity, tensors, or quantum info, this is where the paths cross. Thanks for watching.